Hello, everyone. Welcome to our lecture on computer and network security. I hope everyone is doing well and staying safe. So last time we started discussing blockchains. We basically studied the motivations on blockchains and why we want to overcome the presence of a centralized trusted arbiter. And we said that what we get with blockchain is a distributed system which acts as an append-only data structure, a data structure that you can add to it, but you cannot modify anything in it because all the blocks are actually linked. And we discussed basically the components of a blockchain system, and we started discussing the main cryptographic tools and algorithms that we use, particularly said that we are concerned with hash functions, digital signatures, and Merkle trees. We started discussing how hash functions are used in blockchains. Basically, they assure the integrity of the blockchain itself and all the data and the transactions within. And we discussed the two properties that we are interested in having for a hash function to be used in a blockchain, which is the hiding property and the puzzle friendliness property. We also discussed digital signatures. Basically, this is how a user in the system makes sure that they want to spend a coin, they want to spend a cryptocurrency, they want to transfer funds to someone, and it's depending on the signing a transaction with their private key. And we saw an example of a digital signature algorithm, which is the digital signature standard, and how the signature is calculated and how it is also verified. Now, it is interesting to point out that DSA is not used in blockchains. Actually, an elliptic curve version of it is the one that is used, where basically the signature has or is generated using smaller key sizes but has the same security. One very important feature that we didn't mention in digital signatures is that the public keys that users will have in order to generate the digital signature can actually be used as anonymous identities. Basically, when someone uses a cryptocurrency, quite often they don't want their identity revealed. And so they don't need to have a username or a password or an IP address in the same sense that we would have in other systems. Basically, the public and private keys that are generated, the public key can actually be used as an identity. And so if you want to transfer funds to someone, you don't need to know the name of this person. You just need to know their public key. And this, although it seems that on the outside that this provides anonymity for the user, it can only actually provide pseudonymity. The reason is if someone makes a certain set of transactions, this creates a pattern. So if you only make transactions related, for example, to the purchase of cars, okay, then someone can actually infer from your transaction patterns that you are someone dealing in cars one way or the other. If you do certain types of transactions, someone can infer your identity from that. And that's especially because the blockchain is public. Everyone can actually see all the transactions. If the transactions are indexed by a public key, they don't know your identity, but they can still see all the transactions, and a machine learning algorithm, for example, can figure out how there are patterns in these transactions. So the public key only provides or maintains pseudonymity. Now, technically, you can actually generate more than one public key, and you can divide your cryptocurrency funds over these public keys and actually use several identities in the system, which increases your anonymity in a little bit, but again, it only provides pseudonymity. Okay. Now, so we discussed hash functions, we discussed digital signatures. The third cryptographic tool that we will discuss, and it's actually something that is very important in a blockchain, is called a hash pointer. Now, a hash pointer is very similar to what pointers do in a linked list, except that the hash pointer doesn't just point to where data is stored, but it also includes the hash value of this data. So if you have the figure that you see here in the top right of the slide, the hash pointer points to this data and includes also the hash of the data itself. So it has these two things. It verifies the integrity of the data and it points to where it is stored. Now, using hash pointers, you can actually build this tamper-proof ledger that is called a blockchain. So if you see the figure on the bottom right corner, you see every data block has a header. And the header basically is a hash pointer to the previous data plus the hash of the entire previous block. Actually, the hash of the previous header. So if this is block k minus 2, this is block k minus 1, and this is block k. So block k is the newest block to be published. You see here that block k contains a hash pointer pointing to the block before it, pointing to block k minus 1. And this header in block k contains actually the hash of the header in block k minus 1. So how is this a tamper-proof ledger? It would be a tamper-proof ledger if all the nodes in the system that wish to verify this blockchain only store the hash pointer of the very last block that they have published. So now people don't actually have to store the entire blockchain, they only have to store the very last hash pointer. So how is that? Now let's say there is an attacker who went to block k minus 2 and modified certain transactions or even one transaction in this block. Now, because the blockchain is public, this can be done. But the problem is the hash pointer of block k minus 1 now will not point correctly to the data in block k minus 2, because here the hash pointer actually includes the hash of this data, and so it is no longer going to match the data in block k minus 2. So what can the attacker do? The attacker can then actually change the hash pointer in block k minus 1 so that it matches the transactions that have been changed in block k minus 2. The problem is now the hash pointer in block k is not going to match the block before it, because now the header in block k minus 1 has been changed, and the header in block k points actually to the entire block k minus 1, which includes the header. And so the hash pointer in block k will no longer match. Now, this can be solved if you can also change the final hash pointer, which points to block k. But everyone stores this hash pointer, so the attacker will run into a roadblock. They cannot actually change the last hash pointer because everyone already knows it. It's as if it's a public value. So even though the attacker can go and change the data in k minus 2 and change the hash pointer in k minus 1 and change the hash pointer in block k, they cannot change the final hash pointer of the head of the list because everyone stores it and it is a public value, and so they will not be able to execute this attack successfully. The only way that this attack would be successful is to actually mount a birthday attack, is to be able to find an alternative data block or an alternative value of the data that would match the same hash pointer that everyone has. If the attacker can do that, then the attack would be successful, but we assume that we have a secure hash function that is collision resistant, and so this attack would be computationally difficult to execute. Now, the figure on the bottom left corner shows you what a header actually contains. It contains a pointer to the hash of the previous block header, and it contains the hash of the previous block header as well, and this is how you create a tamper-proof ledger. The figure also shows that the block headers contain something called a Merkle root. Now, the structure that I just mentioned provides a tamper-proof ledger. It provides you with a way to link the blocks together, and so it provides you with a way so that the attacker cannot actually change values within a block. However, if you want to verify that a certain block actually is a member of the blockchain, or a certain block doesn't exist in a blockchain, if we only use this structure, you would have to look actually through the entire blockchain, and you have to save all the blocks so that you can actually verify all the hash pointers later. Now, to avoid having to go through this entire complexity, we use an additional data structure in addition to blockchains, which is called a Merkle tree. A Merkle tree is simply a binary tree that is done with hash pointers. Basically, you take every two blocks and you come up with a data structure that contains the two hash pointers of the two blocks. Okay, this is one level above the data blocks themselves. And then you take the other two blocks and you do the same with their hash pointers. And then you hash these two hash pointers together, you hash these two hash pointers together, and you make up the header at one level above that has the hash. This hash pointer here is pointing to the hash of these two hash pointers, while this hash pointer here is pointing to the hash of these two hash pointers. And then you keep doing that until you reach the root, which is called the Merkle root. This is actually the root of the tree. This is also tamper-proof because if you change the transactions, let's say in this block, then they are not going to match the hash pointer in this level, and it's not going to match the hash pointer in this level, and so it is not going to match the Merkle root. And so if we go back to the structure, we see that every header only stores the Merkle root. And so this is only what you need to search in the Merkle tree. Basically, instead of now having to store the entire blockchain, you only need to store the blocks that would allow you to generate the levels all the way up to the Merkle root. And so in this case, you would be able to validate that a data is a member of the Merkle tree in log n time instead of actually going through the entire blockchain. It provides proof of membership and also provides proof of non-membership if the blocks are sorted. So if the blocks are sorted, let's say every block follows the other, then you can actually check that there is no block between two blocks that are already there, also in logarithmic time. Basically, you compute the hash pointers, and if you find that there is no value between these two blocks, then basically the block that you are testing is not a member of the blockchain. So in cryptocurrencies, we use the blockchain structure, which has hash pointers pointing to the previous block, and this provides a tamper-proof ledger. And we have also the Merkle tree, where you save the Merkle root in every block so that you can actually check the membership in the Merkle tree, and it's also tamper-proof. Now, with that, we have concluded our discussion of all the cryptography techniques that we use in blockchains. Now we can actually see how these tools are combined together to make up a cryptocurrency system. But if we study cryptocurrency system right away, like Bitcoin, it will not be very intuitive because it contains a lot of complicated structures that we would not be able to understand why their developers did it this way from the start. So what we will do is that we will go through simplified cryptocurrencies and we will see how they fail. Now we will start with a simple currency that is called Goofy Coin. Goofy Coin, you have actually a designated entity called Goofy, and this is the only person in the system who is allowed to create coins. So they are allowed to create coins at any time they want. So when Goofy wants to create a coin, they invoke a function that is called create coin, and which gives this coin a unique ID. And then this coin would be digitally signed by Goofy using Goofy's private key to make sure that Goofy is the one who generated the coin. So the presence of a digital signature ensures that only Goofy can create coin because only Goofy has his private key. So he's the only one who can digitally sign the coin. Now, if Goofy would like to give this coin to someone, if Goofy would like to pay someone, they would generate this instruction, pay to Alice, and then the hash pointer here would point to the coin that Goofy would like to pay. So this instruction here says pay to Alice, and here we actually say pay to the public key of Alice, so I don't need to know Alice's name, I only need to know her public key. What do we pay to Alice? Whatever is pointed to by this hash pointer here in the figure. And so to make sure that this transaction is valid, Goofy will also digitally sign the transaction using his private key. And so now what I have is, I have an instruction to pay a coin to Alice that is indicated by a hash pointer. So I know exactly which coin will be paid to Alice. And I know that this transaction is valid because it is digitally signed by Goofy using his private key. Now, Alice now has this coin. If Alice wants to pay this coin to Bob, she can do the exact same. She can say pay to Bob, and then the hash pointer will point to the transaction that Goofy made. So it will point to the transaction where Goofy paid the coin to Alice, and this transaction contains a hash pointer to the coin itself so that you can actually trace through these transactions back to the original coin that was generated by Goofy. And obviously here Alice will also digitally sign the coin. So in this simple currency, we don't actually have a blockchain. We don't have a tamper-proof ledger. Basically, Goofy generates coins, sends them to someone, and then whoever has the coin can then send it to someone else. Now, This shows us actually why we need a blockchain. This is due to something called a double spend attack. Basically, there is nothing that would prevent Alice from generating another transaction that is also digitally signed by Alice using her private key that says pay, for example, to John, and then it points to the same transaction that was given to Alice by Goofy. So what Alice has done in this case is pay the same coin twice, one time to Bob and one time to John. And we know in currencies, we cannot do that. If you pay, let's say 100 pounds to someone, you cannot pay the same 100 pound bill to someone else. You pay it only once. And so the double spending attack is a very serious attack in any currency, and it's something that is definitely should be avoided. And it is the biggest attack that cryptocurrencies try to avoid. And in this simple currency that we have in this example, obviously it is possible. In this case, both Bob and John will think that they now own the same coin, and they can both actually then transfer it to someone else. This is called the double spend attack. And so to get over that, we modify the currency. Let's now have a more advanced currency, which we call Scrooge coin. In Scrooge coin, basically there is still one entity, Scrooge, and he is the only one that generates coins. But now Scrooge maintains a blockchain. Every time there is a transaction, Scrooge adds it to the blockchain, and the blockchain is public. And just as in any blockchain, everyone can actually see it, and everyone only needs to store the head of the list, the final hash pointer in the blockchain. This is the one that everyone can use to verify everything in the blockchain. And so the blockchain is also tamper-proof. And so when Scrooge wants to generate a coin, basically this coin generation is also a transaction that gets added in the blockchain. So there will be a transaction in this block, for example, saying that Scrooge has generated, for example, 3 coins, and this transaction would be digitally signed. So every transaction will be digitally signed and added to the blockchain. Now, if someone wants to send a coin to someone else, let's say we want to do the same thing that we actually did in Goofy Coin. We want to send the coin to Alice, and Alice wants to pay this coin to Bob. So Alice will actually do the transaction in the same way and include the instruction that says pay to the public key of Bob and the hash pointer of this coin. And then she is going to digitally sign this transaction, and then she's going to send this transaction to Scrooge. Now, Scrooge will have the responsibility to validate this transaction. And by validate this transaction, Scrooge has to do 2 things. First of all, Scrooge has to check the digital signature of Alice to make sure that Alice is indeed the one who generated this transaction. And Scrooge also has to make sure that this is not a double spending attack. So Scrooge will have to go through the blockchain and check that this hash pointer that is actually in the transaction has not been used before in the blockchain, and so Alice has not spent this coin before, and because the blockchain stores everything, this transaction would exist. Now notice here that we have 2 hash pointers. We have this hash pointer which is used to point to the previous data block, okay, and we have another hash pointer within the transactions themselves. So we have another hash pointer that points basically to the history of the transaction. So inside the blockchain, you will have a transaction that has a hash pointer that is pointing to a transaction in another blockchain that is pointing to where the original coin was created, for example. Okay, so you shouldn't confuse yourself between the 2 hash pointers. You have one that chains the blocks together, and you have another one that chains the transactions to their history up to when the coin was initially created. In this case, it will be created by Scrooge. So what is the problem actually with this currency? Let's ask ourselves some questions. Can Scrooge actually generate a transaction on behalf of someone else? Can Scrooge, for example, spend the money that Alice owns? The answer is no, because to do that, Scrooge will have to forge the private key of Alice, and it should be computationally difficult to do that. So Scrooge cannot actually generate a transaction on behalf of someone else. Can Scrooge manipulate the transactions or the values of the transactions in the blockchain? The answer is again no, because the blockchain is a tamper-proof ledger. As long as people store the head of the list, the final hash pointer, then we know that modifying the value in one block will make the hash pointer in the next block invalid, and so you'd have to modify that, which makes the hash pointer in the following block invalid, and so on. So Scrooge will also not be able to tamper with the ledger itself. But what is actually the problem with Scrooge coin? The problem here is Scrooge has too much power. Scrooge is the only one who gets to decide which transaction will be published in the blockchain. So Scrooge has the authority to deny someone service. Scrooge can actually tell someone, I'm not going to actually include your transaction in my blockchain, and so your transaction is basically invalid. So Scrooge has this power. Scrooge also has the power to invoke certain transaction fees. He can tell you, for example, I'm not going to include your transaction until you pay me certain amount of money. This would make this system a centralized system that is owned by Scrooge, and this is what we want to avoid in blockchains in the first place. So basically what we want is that we want to have all the features that we saw in Scrooge coin, but in a decentralized way. This is what cryptocurrencies have. Bitcoin and Ethereum and all these cryptocurrencies, they have a decentralized blockchain. And so once we decentralize Scrooge coin, basically we will decentralize the blockchain itself. So we have to ask ourselves these questions. Who will maintain the blockchain? Who gets actually to add a block? Who has authority over which transactions are valid? Who gets to determine this is a good transaction and this is a false transaction? Who is going to create new Bitcoins? And when will these new Bitcoins be created? Who determines the rules of the system change? Who gets to say, I'm going to include now transaction fees, or I'm going to make it more difficult to add blocks to the blockchain, or whatever? And the final question, how do Bitcoins acquire exchange value? This final question is actually outside the scope of our lecture because it is basically up to the demand and supply forces in the market. In 2018, when I first taught blockchains, it was actually the year of the cryptocurrency hype. And so I'm sure you know that cryptocurrencies were in very high value. Now the demand has decreased and their value is no longer the same. So it's just the forces of demand and supply in the market. Let's now try to answer some of these questions. The first thing, how do cryptocurrencies actually maintain a distributed blockchain? Basically, they will rely on an algorithm that is called distributed consensus. Distributed consensus means that all the members of my peer-to-peer network, mainly the miners in my peer-to-peer network, should agree on what the blockchain looks like, should agree on which blocks are actually in the blockchain. Once they all agree on which blocks are in the blockchain, they have achieved consensus. And because they are in a peer-to-peer network, it's a distributed network, this is called a distributed consensus. Okay? So if we read the definition that we see in the slide, if there are n nodes where each node has an input value, some of these nodes are faulty or malicious. A distributed consensus protocol has the following two properties. It must terminate with all honest nodes in agreement on the value, and the value must have been generated by an honest node. So what does this mean? If we read the first line, there are n nodes that each have an input value. In our application, the input value is actually the block. So we have n nodes. These n nodes are actually the miners in my system. Each one of these miners may produce a block. Now, we don't assume that all the miners are honest, and we don't assume that they operate without fault. So some of the miners are faulty and some of them are malicious. Okay? Despite having faulty or malicious nodes, we want all the honest nodes that are actually operating efficiently, the honest miners that are operating efficiently, to agree on which of the blocks that they have produced will be actually added to the blockchain. And obviously, the block that is added to the blockchain should have been generated by an honest node. What do we mean an honest node? It means that all the transactions or all the data in this block are valid transactions. There is no invalid transaction in a generated block. Or it means that the miner does not add invalid transactions in the block that they want to add to the blockchain. Okay, so we want to see how cryptocurrencies actually achieve that. Let's now take a look at the detail. In the figure that you see in the bottom right corner of the slide, you see here Bob. Bob says, I want to pay Alice 5 cryptocurrencies. Okay, so when Bob creates this transaction, Bob simply broadcasts it through the network. Bob actually sends it to everyone in the peer-to-peer network, all the miners. Now, the interesting thing is, Alice doesn't need to be part of the network to receive the transaction. Bob can just actually dedicate 5 Bitcoins, for example, to Alice, and this transaction will be added to the blockchain, and Alice can actually use these coins whenever she wants, but Alice doesn't have to be part of the network. Obviously, it would be a good idea if Alice is a part of the network in order for her to use these Bitcoins, but she doesn't have to for Bob to create this transaction. That's the first thing. So Bob creates a transaction and just broadcasts it in the network. That's the first thing you have to note. Because this network is a peer-to-peer network, the transaction doesn't reach everyone instantaneously. Any peer-to-peer network has certain delays. So Bob, for example, will first send the transaction here, and then it is forwarded to another node, and then another node. So eventually, everyone in the network should receive it, but this may happen actually after a long period of time. Now, this transaction will reach the miners, or at least it will reach the miners over a period of time. Each miner will keep a log of the transactions that they receive. We will receive one transaction from Bob, one transaction from John, one transaction from Mike, and they will keep these transactions in a log, in a sort of like a buffer. And then after a period of time, the miner will now put all these transactions in a block and attempt to publish this block in a blockchain. Okay. Now, let's say you have the miner X. Okay. Now, the miner X has now accumulated enough transactions to generate a block, and now X would like to publish this block. Now, what will X do? X will actually broadcast this block to the peer-to-peer network as well. Okay. Now, it could be the case that you have another miner Y working on a block as well. So Y is also receiving transactions. And because it's a distributed peer-to-peer network, Y may receive some common transactions with X and some different transactions as well. So the transactions that end up in the block generated by Y may not be the same as the transactions in the block generated by X. If they were actually the same, then it would make no difference who generates the block, but they are not. And so Y will also make up a block and broadcasted in the network. The other miners, let's say miner Z, now has to make a choice, either to include or confirm the block that was sent by X or the block that was sent by Y. So let's say this is the current blockchain. Let's say the current blockchain only has 3 blocks, and now we are going to add either the block that was generated by X or the block that was generated by Y. So Z will either confirm the block by X or the block by Y. How will they confirm? By simply adding the block to the blockchain. So if Z adds the block that was generated by X and starts to build on top of that, that means that Z has confirmed the block that was generated by X. If Z adds the block generated by Y and then builds on top of that, and the next block that it sends is actually the building on top of the block generated by Y, then Z would have confirmed the block generated by Y. So the miners will generate the blocks and just broadcast them in the network, and then some of these blocks will be orphaned, meaning that they will be ignored. The other miners will actually ignore them, and some of the blocks will be confirmed by the remaining miners. And by confirmed means that they will start to build their blockchain on top of these blocks. Now, that means that at any time, the miners can actually be seeing different versions of the blockchain. This is actually fine because eventually the distributed consensus algorithm will converge, meaning that the miners will start seeing the same blockchain. Okay. Eventually there will be orphaned blocks, but that's also fine. These blocks can actually be thrown away, and the transactions that were in these blocks that didn't make it in the blockchain will actually make it in a later block. So another node altogether, for example, there could be another node W that also receive the same transactions or some of the same transactions of Y, and they will actually include these transactions in a later block. So having an orphan block is not a big deal at all. Okay, so what does this actually achieve? Let's ask ourselves some questions. Can we steal Bitcoins using this distributed consensus mechanism? Well, it's the same. as in Scrooge coin and in Goofy coin. In order for someone to steal Bitcoin, you have to actually forge a digital signature of someone. What happens actually in a cryptocurrency when someone generates a transaction and broadcasts it in the network? Everyone who receives this transaction must actually validate it. They must check that the digital signature is valid, and they must check that it is not actually existing in the blockchain. Okay, so stealing Bitcoins is not possible. What about denial of service? Can a certain miner, let's say miner X, decide to deny service to Bob? Can miner X, for example, tell Bob that I am not going to include your transactions in any block that I generate? The answer is yes. The miner can actually say that. But is this a problem? The answer is no. Because even if a single miner denies service to Bob, there are so many other miners in the network and they have no reason to do the same. So they can then include the transaction on behalf of Bob. So if one miner acts in a dishonest way, there are actually other miners in the network that can do an honest actually operation. Okay, so a denial of service attack is also very difficult to execute. Now let's take a look at the double spend attack, which is, as we said, is the most important one in cryptocurrencies. So can we execute a double spend attack using this distributed consensus mechanism? Let's consider this scenario. Alice creates a transaction to pay Bob for some kind of service. Let's say Bob has a website and Alice wants to download software from Bob. So Alice sends Bob some Bitcoin, for example, and now Bob should give Alice a link to download the software. Okay. Now, Alice is a malicious user, so she sends these Bitcoins to Bob, but she also creates another account, okay, another public key, and then she transfers the same coins that she sent to Bob to herself. So Alice then generates two transactions. One transaction says transfer 5 Bitcoin to Bob, and the other transaction says transfer the same 5 Bitcoin that were transferred to Bob to another account that is also owned by Alice. So in a sense, Alice has paid herself. Okay. Now let's see if this attack will actually work. Let's say that the first transaction where Alice transferred 5 Bitcoin to Bob is broadcasted in the network. Some nodes actually receive this transaction and include it in their block. The other transaction that Alice actually broadcasts is also in the network, and other nodes may receive it. If these nodes have received the same transaction to transfer the 5 Bitcoin to Bob, they can actually ignore the second one. But some nodes will only receive the second transaction where Alice is transferring funds to herself. And so these nodes have no way of knowing up to this point that this is a double spending attack because the first transaction where the funds were transferred to Bob have not yet been confirmed. They have not been yet added officially to the blockchain. And so the other nodes will think that the second transaction is also a valid one, and they will now try to add it to the blockchain. So now you have a situation where you have two different broadcasted blocks. One contains the valid transaction to Bob, and one contains the malicious transaction that Alice created to herself. Which one will end up making it in the blockchain? No one can actually say. It's a random process. It could be that the valid transaction will actually make it to the blockchain, and it could be that the false transaction will actually be the one that other miners will build on top, and this is the one that is actually going to make it to the blockchain. Okay, so how does Bob prevent himself from being subject to this attack? Simply, Bob will have to wait for a confirmation from the network that their transaction has been added in a block and the block has been added to the blockchain. Confirmation means it has to wait for enough miners to start building on the block that contained their transaction. So this transaction where 5 Bitcoin is transferred to Bob is received by many miners and they will all start working on the next block. Okay. Let's say one of them succeeds and actually finalizes a block and broadcasts it in the network. Other miners will start now building on the block that contains Bob's transaction. How many miners will do that? The more miners start building on the block, let's call it actually block A, the more miners that build on top of block A, the more comfortable Bob should feel that the transaction is now part of the blockchain. And so Bob should wait for confirmation. Bob should wait for enough miners to start actually building on block A. Once Bob sees that, let's say 2, 3, 4, 5, 6 miners are building on block A, Bob can now be comfortable that block A has now become part of the blockchain and the transaction is now valid. And then Bob can actually give Alice the link. Okay. If Bob doesn't do that, if Bob doesn't wait for confirmation, then Bob will be vulnerable to the double spend attack that Alice can actually execute. In Bitcoin, the default number of confirmations is actually 6. Now, 6 is not a magic number. It's not a mathematically proven number. It's just actually a compromise between having to wait too long to make sure that the transaction is valid and between being vulnerable to a double spending attack. So if someone actually receives 6 confirmations, that means confirmations from 6 miners that they are actually building on this block, then we can be comfortable enough that this block is now part of the blockchain. This is actually the protection against double spending attack, and it is shown in this figure. So Alice here generates the transaction to pay Bob, and the transaction contains a hash pointer to where this coin is located in the blockchain. Now Alice will create a second transaction, okay, to pay the coin to herself or to a public key owned by herself, and it is going to have a hash pointer that is pointing to the same location in the blockchain. And now you will have this block and this block containing 2 different transactions, one containing the legitimate one containing the false one. Which one will make it to the blockchain? As we said, this is a random process. Obviously, Bob wants the legitimate one to end up in the blockchain, but he has to wait for confirmations for this to happen. Okay, so this entire distributed consensus mechanism relies on the miners acting honestly, meaning that at least the majority of the miners are mining honestly, that they are including valid transactions to their blocks and that their blocks are honest ones. Okay, how can then cryptocurrencies ensure that the miners are honest? The cryptocurrencies don't attach any moral legitimacy for the miners, meaning that they don't assume that the miners are moral people or ethical people who want to act honestly. Actually, cryptocurrencies assume that the miners will act in their own self-interest. And so, how can you actually design an incentive mechanism to make sure that the miners are acting honestly? Obviously, you cannot penalize a miner for adding an illegitimate transaction. That's not good because the miners have no way of knowing which transaction is a double spend and which transaction is limited. Both transactions are just a transfer of Bitcoin from one public key to another public key, from one user to the other. From the point of view of the miners, all transactions are actually valid. And you cannot reward the miners for avoiding illegitimate transactions as well, because again, they have no way to detect. Instead, Bitcoin and other cryptocurrency functions choose a reward mechanism. So a reward is given to the miner that publishes a block in the blockchain. So whenever a miner succeeds in having a block added to the blockchain, they will get a reward. When will they get this reward? When enough miners provide confirmation. In Bitcoin, again, there are 6 confirmations. So when a miner gets 6 confirmations that 6 other miners have included their block in their blockchain, okay, they get the reward. So what then should this reward be? This is where the application of blockchain in cryptocurrencies become different from the application of blockchains in any other type of system. In cryptocurrencies, because we already are dealing with finances, the reward is actually in the same currency of this cryptocurrency. If you're using Bitcoin, you get Bitcoins as a reward. So when a miner succeeds in publishing a block in the blockchain, they get a set of Bitcoins. Now, initially, when Bitcoin was first created, the reward was 50 Bitcoins. But this reward is being halved. Every about 4 years, the reward gets halved. So 50 became 25. Now, the reward for publishing a block in the blockchain is actually 12.5 Bitcoins. And there is another halving event that is expected this year around May. When is the reward halved? The reward is actually halved every 210,000 blocks, which takes around 4 years to produce, because a block in Bitcoin is produced every around 10 minutes or so. So around May, the reward for publishing a block will be 6.25. This is actually a geometric progression. By 2140, the reward will be almost zero, and all possible Bitcoins will be created. The total sum of Bitcoins that will be created is actually 21 million Bitcoins. So once this happens, will miners actually not have any incentive to add blocks or to mine blocks? The answer is no. There is actually another way to make money in Bitcoin. This is actually called the transaction fee. So when Bob wants to transfer money to Alice, they create this transaction. Let's say Bob wants to transfer 5 Bitcoin to Alice. Bob will actually create the transaction that says, I want to transfer 5 Bitcoin, and there is a transaction fee of 0.2. Basically, Bob is providing a reward for the miners. Whoever gets to include my transaction in your block and gets to successfully publish their block as part of the blockchain, they will get the 0.2 Bitcoin as a reward. Now, you have to note that this transaction fee is not dedicated to a particular miner. The transaction fee is a reward for whoever is going to be successful in finding the next block. Now, is the transaction fee mandatory? The answer is no. You can actually set the transaction fee to zero. But the miners are actually free to include which transactions in their block. They have a set of transactions that are broadcasted in the network. They get to choose which transactions to include. So obviously the miners will have an incentive to include those transactions that have a higher transaction fee, because if they are successful in publishing the block, they will get to collect all these transaction fees as a reward. Okay. So even if all Bitcoins are now produced and there is no more reward for generating a block through getting Bitcoins in this way, there will still be transaction fees to collect. Okay. Now, how does this actually guarantee honesty? The nodes have an incentive to publish a block that will be added in the blockchain. The nodes have no incentive to publish a block that will be orphaned. So the miners now have the incentive of choosing the transactions that will not create a risk for them to be rejected by others. If a miner includes a transaction that is illegitimate, there is a chance that other nodes will actually detect that this is an illegitimate transaction and will throw the block away, will not actually accept the block, and will start building on another block from another mine. This is how it incentivizes the miners to be honest. They want actually to include the legitimate transactions so that they can find a legitimate block, so other nodes can accept it, so they can get a reward in the end. Now, the other thing is we want to keep this Bitcoin or the blockchain system distributed. We don't want a monopoly. We don't want to end up with the Scrooge coin scenario where Scrooge gets to decide which transactions get to be added. So we want to keep the system distributed. We want to avoid monopolizing the system. Basically, to do that, we want to have the node, or we want to choose the node that proposes a block in a way that is random. We don't want to have one node or one miner in the network having a better chance to publish a block than the other. So you need to be able to choose the miner that publishes the block in a way that ensures the system stays distributed. So when the developers of Bitcoin wanted to guarantee that, they started to think about which resource is actually not owned by anyone. Shall we, for example, say that the one that has the most Bitcoins is the one that's going to produce the next block, meaning the rich gets richer? Or shall we actually choose a resource that doesn't belong to anyone? And this is exactly what they did. They chose computing power as the resource. Basically, everyone has computing power. Some people have more computing power than the others, but everyone actually has access to computing power. And so to publish the next block, every miner has to show a proof of work. Every miner has to solve what is called a hash puzzle. And the hash puzzle has medium difficulty. It's not easy to solve, and it's not very, very hard to solve. It has medium difficulty that it can be solved by someone. The difficulty is actually on the order of 10 to the power 20. This is actually a very high difficulty if you look at a single computing device, which is why what people do is that they pool their computing power in what is called mining pools, and all of them work on producing the next block. So what is a hash puzzle? Basically, to produce a block, the miner has to concatenate all the transactions in this block and then concatenate with them the hash of the previous block and then concatenate with them a nonce. How does this actually become a hash puzzle? Basically, it says that I want that when you hash all of these items together, the result is less than a certain target. Okay? And we know from the puzzle friendliness property that if the hash function is puzzle friendly, then the only way to find the nonce that achieves this target, where the output of the hash is less than this target, the only way to do it is brute force. And so by setting an appropriate target, you can set up or you can determine the difficulty of solving the hash puzzle. If the target is very large, then obviously there are so many values of the nonce that will produce a hash output that is less than the target. If the target is very, very small, then there will only be a very small number of nonces that will result in a value that is less than this target. And so by adjusting the value of the target, you can adjust the difficulty of solving the puzzle. And this is exactly what happens in Bitcoin. The miners keep trying in a brute force way different values of the nonce until they find a value that achieves the target. And this is when they can publish the block. And if the block is accepted, it becomes part of the blockchain and they get a reward. You have to note here that this actually requires a lot of computing power, which is why when Bitcoin became very popular 2 years ago, everyone was buying these graphic cards so that they can use GPUs to just evaluate hash puzzles. Okay, now the thing is, you can actually put a lot of computing power and find a nonce that is less than the target, but there is another miner that is also doing the same that beats you to it. So your computing power can actually be wasted in this case. This is why doing cryptocurrency mining is basically like gambling. You are gambling against everyone's computing power in the world, and there's no guarantee that you will be the one who finds the next block, and there is no guarantee that your block will then be accepted in the blockchain. Okay, now the question now is, does this target remain constant throughout the operation? The target determines the difficulty. Now in Bitcoin, we want a block to be generated every around 10 minutes. Again, the 10 minutes is not a magic number. It is just for the efficiency of the network. We don't want to keep producing blocks because then the blocks will contain only very few transactions and we'll end up with a very large number of blocks that becomes more difficult to maintain. So we want to produce a block every around 10 minutes. The target or the value of the target in the hash puzzle is the one that guarantees that. Okay, if there are a very large number of miners in the network, as the number of miners increase, the probability that one of them finds a nonce that achieves the target increases as well. And so what happens is the value of the target is adjusted based on the number of miners in the network. Basically, the number of miners keep increasing, and so the value of the target keeps decreasing to increase the difficulty. So that at the end, the value of the target is adjusted to make sure that there is actually a block that is found only in about every 10 minutes. Okay, this slide here shows how you actually try nonces. So you try one, you check if it's less than the target. The answer is no. You try another one until you actually find one that achieves the target. This figure here is from a website that is called the Bitcoin Explorer. You can actually check it out yourself. This shows the Bitcoin difficulty over time. I included this slide from 2018, but you can actually check the current one on the website if you want. Okay. Okay. Now the question is our system actually really distributed? If everyone was actually mining independently, the answer would be yes. But in reality, this is not what happens. What happens is there are actually organizations that run what are called mining pools, as we discussed. Okay. What you do is, if you want to become a miner, you subscribe to this mining pool. You become a member of this mining pool. Basically, the mining pool is responsible for gathering transactions, and your role as a miner is just to calculate their nonces. Okay. And then if you find a block and this block gets accepted in the system, the reward is now divided over everyone in this mining pool. Without that, it would be very difficult for someone to find a correct nonce on their own, because every laptop, every computer has a very limited computing power. You will see in this figure that some mining pools are bigger than others, and these big mining pools, unfortunately, have bigger control of which transactions are added, and so they reduce the degree of decentralization in the system. This is actually just the reality of the situation. Okay, so what happens if a block is not accepted? Basically, it means that the transactions in this block are not actually added to the blockchain. If these transactions are actually added in another block, that is fine. But if they are not, then the same miner will actually include these transactions in a later block. And so it could be the case that you have what is called a fork in the system. Some nodes are mining over B1 dash, some nodes are mining over B1. Eventually, the miners will just see where is the longest blockchain and will just continue mining on top of this longest blockchain. And the other one will be a fork and it will be orphaned eventually. Okay. Now let's look at a drastic situation to see what is actually the worst case scenario. One of the scenarios that people think about is what is called the 51% attack, which basically says that you have an attacker who controls 51% of the total mining power of the network. A very important, a very big mining pool that now controls over 50% of the total mining power. Now let's see what this attacker will be able to do and what they will not be able to do. Now, can an attacker generate a fake transaction? The answer is no, because to generate a fake transaction, they will need the private key of someone. Obviously, they can generate a fake transaction and just add it to their own blockchain. But the honest nodes will detect that this is a fake transaction and will reject it. So the attacker will not be able to convince the 49% that this is actually a fake transaction. The 49% will be convinced that this is actually a fake transaction and they will ignore it. Okay. Can the attacker create the longest blockchain? The answer is yes. The attacker can create the longest blockchain if they include fake transactions in it, but the honest nodes will not actually build on top of this longest blockchain because they will not verify the signatures in these transactions. So now the honest nodes will start rejecting this longest blockchain, even though it is the longest blockchain, but because it contains fake transactions. So the attacker cannot actually force the honest nodes to accept the longest blockchain and cannot generate fake transactions as well. Now, eventually, the honest nodes will keep building on top of their own version of the honest blockchain. They will keep including the honest transactions and will keep building on top of the honest blockchain. And now a fork will be created. You will have the blockchain that is generated by the attacker, and you have the blockchain that will be generated by the honest nodes. And you will not be able, the attacker will not be able to convince the honest nodes to accept the longest blockchain. So in this sense, the 51% attack will not succeed. But what would the attacker actually be able to achieve? What will they be successful in doing? The attacker will be able to destroy confidence in the system. If you know that a certain cryptocurrency has this type of attack, you will not want to invest your money in it because you will not be sure whether your transactions will make it there or not, or whether someone can actually steal your Bitcoin or not. This is actually a big part of most financial systems. If you don't trust in an institution, it is unlikely that you will trust them with your money. And this is what the 51% attack may succeed in doing. Okay. Finally, we'll just talk a little bit about the peer-to-peer network in Bitcoin itself. It is just a flat peer-to-peer network running on TCP. When you want to join, you select a seed node, just a member of the peer-to-peer network, and you establish a TCP connection with it. You actually use DNS to discover the seed node, and you just pick one, and you start actually forming connections with some of the neighbors, and you pick this seed network at random. So at the end of the day, the peer-to-peer network is flat and it's actually containing random connections. There is no specific structure for it. Now, the peers in the network, they perform these two functions. They validate and they propagate transactions, and they validate and they propagate blocks. Validating transactions consists of these four things. They have to validate that the transaction with the current blockchain. This ensures that there is no double spend attack. They validate that they didn't hear this transaction before, otherwise they will have to ignore it. And they validate the digital signature in the transaction as well, and then they can propagate this transaction to the next node. Now, we know that due to network latency, not everyone receives the transaction right away. Okay, they do the same thing with blocks, but validating blocks is more complex. They have to validate the nonce, they have to validate every transaction in the block, they have to validate the hash pointer, and they have to validate that there is no double spending attacks there. This slide here just shows an example of a block. You can see here this block contains 2,315 transactions. This is actually the value of the nonce that the miner created, and this was the difficulty when the block was actually generated. And these are the transactions that are contained in the block. You will see here that the first transaction is actually called the Coinbase. This is the reward that the miner will get. These are the newly generated coins, and this is the only way that coins are newly generated. These are the newly generated coins that will become the reward of this miner. You see here that it's actually 13.02. It's actually 12.5 plus the total transaction fees that are accumulated in the block. Okay. Every node in the peer-to-peer network can either be a full validating node or a simple payment verification system. The fully validating node are the ones that store the blockchain, they maintain the history, they validate blocks and transactions. The SPV node, the simple payment verifications, are the ones that we use when we just want to do a transaction. We don't want to be a miner. We don't actually want to validate anything. We don't want to dedicate computing power. We just want to be able to pay money and exchange finances with someone. Okay. That's it for blockchains. Starting next time, we will actually be going into a new topic. I wish you the best of luck, and I hope you will stay safe. Thank you very much.